Tonight, when you close your eyes, the sky above your roof will be full of stars. Hundreds of billions of them in our galaxy alone. Around most of them, worlds. More planets than there are grains of sand on every beach on Earth. And from all of it, every star, every world, every direction, for as long as we have known how to listen, we have heard nothing. Not one voice, not one machine, not one repeated whisper that we could not explain away. The universe, which should by every reasonable count be crowded, is silent. Scientists have a name for this problem. It started as a casual question, asked over lunch in the summer of 1950 by one of the greatest physicists who ever lived, 4 men at a table in the mountains of New Mexico. A joke about flying saucers. And then, out of nowhere, a question so simple that everyone laughed, and so heavy that nobody has been able to put it down since. Where is everybody? Tonight we follow that question all the way out. The lunch where it was born, the equation written on a blackboard to tame it. The one night in 1977 when, for 72 seconds, something almost answered, and the strange family of explanations, some lonely, some hopeful, some quietly unsettling, that scientists still argue about right now, this year, over a small ocean world 124 light-years away. If these slow journeys help you rest, subscribing is the easiest way to drift out with us again. Settle in. We begin with lunch. In the summer of 1950, in the high pine country of northern New Mexico, 4 physicists walked to lunch. The place was Los Alamos, the laboratory in the mountains where, only a few years earlier, the atomic bomb had been built. The war was over now. The town had settled into something almost ordinary, a company town of scientists, with schools and gardens and a stone lodge where people ate lunch. The 4 men walking toward that lodge were Enrico Fermi, Edward Teller, Emil Konopinski, and Herbert York. 3 of them would live long enough to be asked, decades later, what exactly was said that day. Their answers, gathered into a quiet government report in 1985, are how we know this story at all. Fermi was the famous one, an Italian Nobel laureate, builder of the first nuclear reactor, a man so celebrated for estimating impossible things in his head that the whole style of calculation now carries his name. Colleagues called him the last physicist who was great at both theory and experiment. When Fermi asked a question, even a playful one, people listened. Fermi stood up as the shockwave approached and let a handful of small paper scraps fall from. The summer of 1950 was the height of America's first flying saucer craze. Newspapers were full of lights in the sky. One of the men remembered a cartoon from the New Yorker magazine, which blamed a small mystery in New York City, public trash cans that kept disappearing, on little visitors from space hauling them away to their saucers. The 4 physicists laughed about it. They agreed, as scientists mostly did, that the saucers were not real. Then, as they walked, Fermi turned the game serious in the way only he could. He asked Teller something like this: what is the probability that within the next 10 years we will have clear evidence of an object moving faster than light? Teller, no shrinking violet himself, guessed 1 in a million. Fermi shook his head. That is much too low, he said. The probability is more like 10%. The others knew his habits well enough to smile. 10%, among Fermi's friends, was the well-known figure for a Fermi miracle. The conversation drifted on to ordinary things. The men reached the lodge, sat down, ordered lunch. The flying saucers were forgotten, and then, in the middle of the meal, apropos of nothing at all, Fermi looked up and asked, moving faster than light, Teller, no shrinking violet himself, guessed 1 in a million. The table burst out laughing. That is the detail every witness agreed on, the laughter. Herbert York remembered that somehow, despite the question coming out of nowhere, everyone at the table knew immediately and exactly what Fermi meant. He was not asking about colleagues missing from the dining room. The men reached the lodge, sat down, ordered lunch. The flying saucers were forgotten. Because here is what was sitting underneath those 4 casual words. The galaxy is enormous, but it is also old, billions of years old. And Fermi, being Fermi, began running numbers out loud right there over lunch. How many might have planets? How long it would take a civilization, even one only modestly more patient than ours, to spread from star to star? The numbers in his head all pointed the same direction. If technological life were at all common, then someone, somewhere, should have arisen long before us with millions of years of head start, time enough to cross the galaxy many times over. They should have been here long ago. The Earth should have been visited, perhaps settled, before humans ever existed. How many might have planets? How long it would take a civilization? It had, as far as anyone could tell, always been empty. York recalled that the lunch ended with a shared feeling that the question was strong, and that no one at the table had answered it. Someone may have floated the dark idea that technological civilizations destroy themselves, and this was, remember, a table of men who had built the bomb. The Earth should have been visited, perhaps settled, before humans ever existed. And yet, the afternoon sky over the mesa was empty. It had, as far as anyone could tell, always been empty. York recalled that the lunch ended with a shared feeling that the question was strong, and that no one at the table had answered it. Someone may have floated the dark idea that technological civilizations destroy themselves, and this was, remember, a table of men who had built the bomb, on the eve of building a far bigger one. But York was clear that there was no mood of doom. Fermi himself reflected that the world had, on the whole, grown better over the previous 50 years, with less slavery in it now, and less disease. The question was left open, like a window, and the men went back to their work. Fermi died 4 years later, in 1954, without ever writing down a word about that lunch. He never knew he had founded anything. For 25 years, the question lived only as a story physicists told each other. A famous man's famous remark, until other scientists picked it up, sharpened it, and gave it the name it carries now. The Fermi paradox. A paradox because both halves seem true, and they cannot both be true. The universe should be full of others, and the universe looks empty. There is something fitting for a night like this in how gently it began. No telescope, no discovery, no alarm, just 4 friends at lunch, a joke about trash cans, and a question simple enough for a child, asked by a man who could weigh the galaxy in his head between the soup and the coffee. But a question is only as strong as the numbers behind it, and in the decades after that lunch, the numbers did something nobody quite expected. They got worse. Every new thing we learned about the universe made Fermi's question heavier, not lighter. Just how heavy, just how crowded the universe ought to be is where we drift next. To feel the weight of Fermi's question, you have to feel the size of the sky. Not as a number on a page, but slowly, the way you might walk the length of a shoreline instead of reading it on a map. Start with our galaxy, the Milky Way. On a truly dark night, far from city light, you can see it as a pale river of haze arching overhead. Every part of that haze is stars. Our galaxy holds somewhere between 100 billion and 400 billion of them. The honest answer is that we have not finished counting. and the counting is hard precisely because there are too many to count. Try to hold 100 billion of anything in your mind. If you began counting stars tonight, one per second, never sleeping, never stopping, you would still be counting 3,000 years from now. The pyramids would be young compared to your counting, and that is one galaxy. Beyond ours, the deep surveys suggest hundreds of billions of galaxies more, perhaps as many as 2 trillion, each carrying its own billions of stars. The arithmetic stops meaning anything. It becomes weather, an ocean, a thing you float in, rather than measure. Now, when Fermi asked his question in 1950, there was one great unknown hiding in those numbers. Stars were certain, planets were not. In 1950, not a single planet had ever been found outside our solar system. For all anyone truly knew, planets might be rare freaks of cosmic luck, and Earth might be one of a handful in the whole galaxy. That hope, if you want to call it that, lasted until 1995, when astronomers in Switzerland caught the telltale wobble of a star called 51 Pegasi, tugged by an unseen world. The first planet ever found around another sun like ours. The dam broke. Within a generation we went from 0 known worlds beyond our solar system to roughly 6,000 confirmed, with thousands more candidates waiting. A space telescope called Kepler stared at a single small patch of sky for years, watching for the tiny dimmings of starlight that mean a planet is crossing its star, and what it found settled the old question forever. Planets are not rare. Planets are the rule. Most stars have them. Many stars have several, whole families of worlds like ours. And when astronomers ran the statistics on Kepler's patch of sky, the result was the kind of number you should only encounter while lying safely in bed. In our galaxy alone, the count of rocky worlds orbiting in the comfortable zone around their stars, not too hot, not too cold, where water could lie liquid on the surface, comes out in the billions. Billions of places where, as far as physics and chemistry are concerned, rain could fall and seas could form. The nearest of them is almost embarrassingly close. Proxima Centauri, the nearest star to the sun of all, just over 4 light-years away, has a planet at least the size of Earth sitting in its warm zone, the very first door out of our solar system, and there is already a world behind it. So let yourself feel what this does to Fermi's lunch question. In 1950 he asked it knowing only the stars. We get to ask it knowing the planets too. Every single piece of knowledge we have gained since that lunch has pushed in the same. Direction, more worlds, more chances, more time. It is ancient, more than 13 billion years old, and many of its stars and worlds formed billions of years before the sun was even a cloud of drifting gas. There are planets in our galaxy that were already older than Earth is now before Earth existed. Billions of years of head start on billions of stages. If life arises even rarely, even one world in a million, the galaxy should hold thousands of living planets. If even a small fraction of those ever produce minds, and a small fraction of those minds build machines, then the night sky you fall asleep under has had billions of years to fill itself with voices, with engineering, with travellers. We're not asking the universe for a miracle. We are asking it for one success story older than us. One. And here is the other side of the ledger. The side that makes the silence strange. We have been a loud species for only about a century. Since the first powerful radio transmitters, our broadcasts have been leaking off this planet at the speed of light, an expanding bubble of voices and music and static, now a bit more than 100 light-years deep. That sounds vast. Against the 100,000 light-year width of the galaxy, our bubble is a droplet. If the Milky Way, were the size of a continent. Everything humanity has ever said would so far fill a single small town. So we are quiet, and new, and that is forgivable. But the others, if there are others, have no such excuse. They have had geological ages to speak, to travel, to build things big enough to notice. The numbers say they should exist. The clock says they have had time beyond imagining. And the sky says nothing. That contradiction has a name among astronomers, one of the loveliest and loneliest phrases in all of science. They call it the Great Silence. But before anyone could call the silence great, somebody had to actually listen, and the story of the first human being, who pointed a dish at another star and genuinely listened, half hoping, begins with two physicists and a single sheet of paper in 1959. 9 years after Fermi's lunch, the question finally left the lunch table and entered science. It happened, as these things often do, quietly, in the back pages of a journal. In September of 1959, the British journal Nature published a short paper by two physicists at Cornell University, Giuseppe Cocconi and Philip Morrison. Searching for interstellar communications, the idea inside it was anything but. The two men had asked themselves a beautifully practical question. Suppose, just suppose, there are civilizations out there among the stars. Is there any way, with the instruments humanity already owns, that we could hear them? Their answer changed everything, because their answer was yes. Radio, they pointed out, crosses interstellar distances easily. It moves at the speed of light, passes through the dust between stars, and costs comparatively little to produce. A powerful transmitter aimed with a large dish could be heard across hundreds of light years by a receiving dish no bigger than the ones radio astronomers were already building. For the first time in human history, two worlds that had never met could, in principle, speak. But the sky is wide and the radio dial is wider. Where would you even tune? And here Cocconi and Morrison produced the insight the whole field still rests on. Hydrogen, they said. Hydrogen is the most common atom in the universe, and it hums. Every cloud of cold hydrogen drifting between the stars gives off a faint natural tone at one, very precise frequency, 1420 megahertz, a wavelength of 21 centimeters. Every radio astronomer on every world would discover that tone early, because it is the loudest natural marker on the entire dial. It is the one frequency that every civilization that ever builds a radio telescope is guaranteed to know. If you wanted to be found, you would call out there beside the hydrogen line, in the quietest part of the radio sky. So that is where we should listen. The two physicists ended their paper with a sentence that has become a kind of scripture for everyone who has ever pointed a dish at the stars. The probability of success is difficult to estimate, they wrote, but if we never search, the chance of success is 0. As it happened, someone was already preparing to search. A young radio astronomer named Frank Drake, not yet 30, working at the brand new National Radio Astronomy Observatory in Greenbank, West Virginia, had been quietly nursing the same idea on his own, almost afraid to say it out loud in case it ended his career. When the Cocconi and Morrison paper appeared, it gave him cover. The observatory's director agreed to let him try. And so, in the spring of 1960, in a green valley folded into the Allegheny Mountains, chosen for the radio quiet of its hills, the first true search began. Drake named it Project Ozma, after the princess of the imaginary land of Oz. Very far away, difficult to reach, and populated by strange and exotic beings. There is something wonderful in that choice. The most serious experiment imaginable, named for a children's book. The instrument was an 85-foot dish, modest even by the standards of its day. The targets were 2 stars, chosen because they were the nearest reasonable suns, similar to our own, about 11 and 12 light-years away, Tau Ceti in the constellation of the Whale. Epsilon Eridani in the river. For about 2 months, 6 hours a day, Drake tuned to the hydrogen line and listened, through headphones, to the static of other suns. A young man in a quiet valley doing something no human being had ever done before, genuinely listening. And on one of the very first days the universe played a joke on him that, in hindsight, reads like a warning shot for the whole field. The dish was pointed at Epsilon Eridani when the receiver erupted, a strong pulsing signal, 8 sharp bursts per second, booming through the headphones, exactly the kind of thing they were listening for. For a few electric minutes, the handful of people in that control room sat with the possibility that it had happened, immediately, on practically the first try. Drake later admitted his first feeling was not triumph, but a kind of dizziness. Nobody had prepared a plan for success. Was he supposed to call the government? The newspapers? Who do you even tell? Then the test. If the signal came from Epsilon Eridani, it should fade. It boomed on, just as strong, from empty sky. The source was terrestrial after all, almost certainly a military aircraft system. Human noise leaking into the silence. The lesson stuck, and it has been relearned by every searcher since. The sky is full of false voices, and nearly all of them are ours. Project Ozma heard nothing else. 2 months, 2 stars, 1 false alarm, and silence. As a search, it was almost laughably small, 2 grains of sand from an entire shoreline. But as a beginning, it was everything. Before Ozma, the silence of the universe was a philosophical mood. After Ozma, it was a measurement, something you could do science about. The great silence had become an experimental result, with a date and an instrument attached. Drake understood that one young man with one dish was not an answer, but an opening move. What the new field needed was to think, carefully and together, about what the search was really looking for, and how much hope was mathematically reasonable. So the following year he invited a dozen remarkable people to that same green valley, and prepared, as a simple agenda for the meeting, a single line of symbols that would become one of the most famous equations ever written, that blackboard is next. On the morning of the 1st of November, 1961, in a cosy residence hall at the Green Bank Observatory, about a dozen people gathered around a long table with their coffee. They had come quietly, at the request of the National Academy of Sciences, and there was no press, and almost no paper trail. The question on the table was simple to say, and enormous to answer. Is searching for other civilizations a serious scientific pursuit, or a daydream? The guest list, for such a small room, was extraordinary. Philip Morrison, whose paper had opened the field, Frank Drake, who had done the first search, and who had organized the gathering, a young planetary astronomer named Carl Sagan, just 27, decades before the world knew his name, the biologist Joshua Lederberg, a brilliant radio engineer named Barney Oliver, who flew himself in, more or less self-invited, because nothing on Earth interested him more, and the biochemist Melvin Calvin, who, in the middle of the meeting, was called to the hallway telephone and informed that he had just won the Nobel Prize in chemistry. The little group toasted him with champagne someone had thoughtfully smuggled in, and then went back to discussing the galaxy. Drake had faced a small practical problem while planning the event. A meeting needs an agenda. But what is the agenda for a question nobody has ever answered? In the days before the conference, he sat down and tried to list in order. every single thing you would need to know to predict how many detectable civilizations share our galaxy right now. Not to answer it, just to organize the ignorance. He found there were 7 things, and on that first morning he wrote them on the blackboard as a single line of multiplication. The number of civilizations we might hear from equals the rate at which the galaxy makes. Suitable stars times the fraction of stars with planets times the number of livable worlds per system times the fraction of those where life actually begins times the fraction of living worlds that develop intelligence times the fraction of intelligent species that build technology we could detect times, finally, the average lifetime of such a civilization. He did not leap up and shout Eureka. He said later it was not a discovery at all, just something that had been sitting in his mind for months, obvious once you looked at it. He wrote it the way you might write a shopping list, and yet that line of chalk became the Drake equation, sometimes called the second most important equation in science, and today a plaque hangs on that wall in Green Bank marking the spot where it was first written. Here is the gentle genius of it. The equation answers nothing. What it does is take one impossible question and break it into 7 smaller ones, each of which science can actually chip away at. It is a map of ignorance, drawn so precisely that you can watch, decade by decade, as the ignorance shrinks. In 1961, only the first term, the birth rate of stars, was known at all. Every other term was a blank. Since then, term by term, the blanks have been filling in and, remarkably, every one that has been filled has come back generous. Planets, as we drifted through earlier, orbit nearly every star. Livable worlds number in the billions. The universe keeps saying yes. For 3 days the group argued the 7 terms, and the arguing was warmest at the end of the line. The biologists were optimistic about life beginning, given oceans and time. The fraction that becomes intelligent, the fraction that builds radios. These were guesses dressed in numbers, and everyone knew it. But the term that truly haunted the room was the last one, L, the average lifetime of a technological civilization. Think about what that letter is really asking. Once a world learns to build transmitters, and bombs, and machines that reshape its climate, how long does it typically last? 1,000 years, 1,000,000. And their guesses range from about 1,000 years to 100 million, which is another way of saying nobody had any idea. It was 1961. The Cuban Missile Crisis was less than a year away. When those scientists argued about how long civilizations survive, they were not entirely talking about aliens. Frank Drake himself, looking back across half a century, said the great unknown was still L, and that our own civilization proves only that the minimum value is about 100 years. We are ourselves the only data point in the most important term of the equation, and we are still measurement. Before they parted, the group did one more thing, and it is my favourite detail in the whole story. They gave themselves a name, the Order of the Dolphin, in honour of one attendee's research into whether humans could learn to communicate with dolphins, another intelligence sharing our own planet, with whom we still cannot really hold a conversation. The little joke had a sober centre. If talking across species on one world is this hard, what is talking across the stars going to be? The equation made the search respectable. It gave the question structure and gave the optimists a frame for their hope. Multiply the terms with a hopeful hand, and the galaxy holds thousands of civilizations. The silence in 1961 could still be explained the easy way. Nobody had really listened yet. And so humanity began slowly to listen. Bigger dishes, wider bands, patient surveys through the 60s and 70s, sweeping the hydrogen line where Cocconi and Morrison said the voices would be. And then, one August night in 1977, at a huge and humble telescope in a field in Ohio, while nobody at all was watching, something arrived, the 72 seconds that still have no explanation next. In the flat farm country of Delaware, Ohio, there once stood a radio telescope unlike any other. It did not look like a dish. It looked like a fence built for giants. A vast rectangle of aluminum and wire mesh lying across a field bigger than 3 football pitches, with a tilted reflector at one end and a curved one at the other. The students and staff of Ohio State University, who built and ran it largely on volunteer labour and almost no money, called it Big Ear. Big Ear could not be steered. It pointed wherever the turning of the earth pointed it, a fixed ear against the rolling sky, listening to whatever drifted overhead. By 1977 it had been assigned full-time to the search. Night after night it swept the heavens at the hydrogen line, the quiet waterhole frequency where the first listeners had said a voice would most likely call. A computer sampled the sky and printed the results as columns of numbers and letters on continuous paper, and every few days a volunteer would collect the stack and go through it by hand, line by line, looking for anything unusual. The volunteer was a professor named Jerry Amon, and a few days after the 15th of August, 1977, he was sitting at his kitchen table working through the latest pile of printout, when he stopped. There, in channel 2, running down the page, was a short string of characters, 6EQUJ5. To anyone else on Earth it would have meant nothing. To Amon, it meant the intensity of a radio source rising, peaking, and falling in a smooth and perfect arc. The code was simple. Numbers meant faint. Letters meant strong, climbing through the alphabet. A reading of U meant a signal 30 times louder than the background hiss of the sky. In years of listening, the survey had never recorded anything close to it. And the shape of it was the thing. The signal had risen and faded over about 72 seconds, which was precisely how long any fixed point in the heavens took to drift through Big Ears, beam as the earth turned. That smooth 72-second arc was the telescope's own signature, its way of saying this came from the sky, not from a passing car, not from a local transmitter, not from a storm, from out there, riding the rotation of the heavens. Eman took the red pen he was using, circled the 6 characters, and in the margin wrote a single word: wow. He did not know it, but he had just given the most famous unexplained signal in the history of astronomy its permanent scientific name, the wow signal. Half a century of papers and books and arguments, all carrying a marginal note scribbled at a kitchen table. Now drift through what made the signal so maddeningly good. It arrived at 1420 megahertz, almost exactly the hydrogen line, off by a whisker, the very frequency the field's founders had predicted a deliberate beacon would choose. More than that, by international agreement that band is protected, no one on Earth, and nothing we launch is permitted to transmit there, precisely so astronomers can hear the universe through it. It was narrow, focused at one spot on the dial in the way natural sources almost never are, and it was strong. The signal's home in the sky was in the constellation Sagittarius, toward the rich star clouds near the centre of our galaxy, close to a globular cluster called M55, and when astronomers looked there they found nothing. No nearby star, no planet, no known satellite. Checks of spacecraft records came up empty, and besides, Transmitting there would have been illegal for any of them. One by one, the ordinary explanations were weighed and found wanting. So they did the only sensible thing. They listened again. The signal had appeared on the night of August 15th at 16 minutes past 11 Eastern Time, while no human being was watching, recorded automatically by a machine in a field. Big Ear turned back to that patch of sky the very next night. Silence. It returned to it hundreds of times over the following years. Silence. Other astronomers took up the hunt with bigger instruments, sweeping that coordinate again and again across decades. The sky there has never spoken again. That single fact is the splinter in the story. A deliberate beacon, you would think, repeats. A natural source, you would think, would be found, or recur, or leave kin scattered across the sky. The wow signal did neither. It behaved like a lighthouse beam that swept across us exactly once. Or, if you prefer the humbler readings, like some rare reflection or trick of our own noise that we have never managed to reproduce. Explanations have been offered over the years, comets, reflections, instrumental ghosts, and each has been tested and found to have problems. Among the people who study it most closely, the honest verdict after nearly 50 years remains 2 words long. Here is a small detail to carry towards sleep. That August was a remarkable month for the human species. 5 days after the wow signal arrived, a rocket lifted off from Florida carrying Voyager 2, beginning the journey we followed together on another night. In the same late summer, in the same turning of this one small planet, we sent our farthest traveller out into the dark, and we may, just possibly, have heard something looking back. Or we heard nothing at all, dressed in coincidence. 72 seconds is too short to know. But while the listeners kept listening, a very different kind of mind was circling Fermi's question, not with a telescope but with a pencil and a cold sense of time. His argument would make the silence much harder to explain away. That argument is next. In 1975, an astrophysicist named Michael Hart published a paper with a title so blunt it reads like a verdict, an explanation for the absence of extraterrestrials on Earth. Hart began with the one piece of evidence everyone could agree on, and he gave it a deliberately plain name. There are no intelligent beings from outer space on Earth now. Whatever you believe about lights in the sky, no visitor has stayed. No embassy stands in any capital. No alien machine sits in any museum. The Earth today is ours alone. That is fact A, and like all facts, Hart said, it requires an explanation. Then he did something quietly devastating. He took the warm, optimistic universe of the Drake equation, the one where the galaxy hums with thousands of civilizations, and he asked one cold question of it. If they exist, why are they not here? Not, why have we not heard them? Why are they not here on Earth already? Because here is the engine of Hart's argument, and it runs on nothing but patience. Interstellar travel does not require magic. It does not require breaking the light barrier or bending space. It only requires going, slowly and not stopping. Suppose a civilization sends ships to the nearest stars at 1/10 of the speed of light, a speed that physics permits. The journey takes decades. They build, and after some centuries their daughter colonies send out ships of their own. The wave spreads. Each hop is slow, the sum is not. Hart ran the numbers, and others have run them again and again since, with different assumptions, and the answers all land in the same astonishing range. A single civilization, expanding star by star at achievable speeds, crosses the entire galaxy in somewhere between a few 100,000 and 100 million years, Take the gloomiest version, the slowest ships, the longest pauses. Call it 100 million years to fill the Milky Way from edge to edge. Now set that against the age of the stage. The galaxy is more than 13 billion years old. 100 million years is less than 1% of that, which means the window for someone else to have done this is not narrow. It is almost the entire history of the universe. Any civilization arising anywhere in the Milky Way, at almost any point in deep time, even once, had time to reach every star, including ours, hundreds of times over. The galaxy is not too big to cross. It is, on these time scales, small. That is the part nobody is prepared for. The galaxy is small. And there was a sharper version of the argument still to come. A few years later, the cosmologist Frank Tipler added a refinement borrowed from the mathematician John von Neumann, who had proven on paper that machines can in principle build copies of themselves. Imagine then a civilization that sends out not crews, but a handful of self-copying probes. Each probe arrives at a new star system, mines an asteroid or two, builds several copies of itself and sends them onward. The cost to the senders is one initial investment. The wave that follows feeds itself, doubling and doubling, a kind of slow lightning spreading through the galaxy. With probes like that, Hart's 100 million years collapses toward the bottom of the range. The galaxy explored, catalogued, perhaps quietly observed, within 1 million years or less, well under 1,000th of its age. We, a civilization barely a century into the radio age, already send probes to other worlds. We followed one of them together on another night. An aging traveller with a golden record on its hull. The step from Voyager to a probe that can copy itself is large, but it is engineering, not sorcery. If we can sketch it in our first 100 years, what stops a million-year-old civilization from having done it long ago? Hart went through the alternative explanations one family at a time, like a man checking rooms in a house. Maybe travel is too hard, but it is not, given time. And he showed the time was there. Maybe they choose not to come, every one of them. But it takes only a single exception. One curious culture, one restless colony, one runaway probe, and the galaxy fills anyway. A rule that must bind every civilization that ever arises across billions of years, with no defectors, is not an explanation, he argued. It is a hope. Maybe they came long ago and left. Then where are the traces? Maybe they are simply too young, all of them, everywhere. But the galaxy's stars are mostly older than ours. And so Hart followed his own logic to the end of the corridor, to the conclusion he felt the silence was pointing at all along. They are not here because they do not exist. We are, he suggested, the first, at least in this galaxy. The silence is not a mystery. It is an answer, the most enormous answer imaginable, hiding in plain sight above every sleeper on Earth. Many scientists recoiled, Carl Sagan among them. Who fired back that absence of visitors is flimsy evidence for absence of anyone. The argument has rolled on for 50 years, and it sits at the heart of everything that comes later tonight. But notice what Hart's dare really did. It transformed the silence from a curiosity into a clue. If the galaxy truly is empty, or nearly so, then somewhere between dead rock and starships there must stand a barrier, something that stops almost everything that starts. A quiet economist would later give that barrier a name, one of the most haunting names in science. And the strangest part is this. The name comes with a question attached, and the question is about us. The great filter, next. In 1996, An economist and thinker named Robin Hanson took the silence and asked a question that turns the cold of deep space directly toward us. If the galaxy should be full and it is empty, then something must be stopping life from getting all the way to the stars. He gave that something a name that sounds almost dull and is anything but. The Great Filter. Picture the whole journey, from lifeless matter to a civilization that spreads among the stars, as a long corridor with many doors. The first door is the beginning of life itself, the moment dead chemistry first becomes something that copies itself, then a door for simple cells learning to become complex ones. A door for many cells learning to cooperate as one body. A door for nervous systems, for intelligence, for tools, for language, for technology, and at the far end, a final door, the one no one on Earth has yet walked through. A civilization that lasts long enough, and grows wise enough, to truly reach beyond its own world and endure out there. The Great Filter is Hanson's name for the idea that at least one of those doors is nearly impossible to open. Somewhere along that corridor there is a barrier so severe that almost everything which approaches it stops there. Not most things, almost everything. The silence of the universe, Hanson argued, is the proof that the filter is real and that it is brutal, because if any door were easy, the galaxy would show it, loudly, in voices and engineering and light. Now, here is the move that makes this idea impossible to put down once you have picked it up. The crucial question is not whether the filter exists. The silence strongly suggests it does. The crucial question is where it sits in the corridor. Is the Great Filter behind us, or is it ahead of us? Follow both branches gently, because your answer changes the meaning of everything you see when you look up at night. Suppose the filter is behind us. Suppose the nearly impossible step is one we have already, miraculously, passed. Perhaps it was the very beginning of life, that first self-copying molecule, an event so staggeringly unlikely that on most worlds it simply never happens, and the oceans stay dead forever. Or perhaps it was a later door. On Earth, life appeared remarkably early, but then it stalled as nothing more than simple cells, for around 2 billion years, almost half the age of the planet, before the leap to complex cells finally occurred. 2 billion years stuck at one door. That long pause is, to some scientists, the fingerprint of an almost impossible step, one that most living worlds never get past. If the filter is behind us, then we are the rare ones. The galaxy is empty because the corridor is nearly uncrossable, and against all odds, we crossed. In that reading the silence is lonely, but it is also a kind of coronation. The future is wide open, and it may be ours. But suppose instead the filter is ahead of us. Suppose life is common, and intelligence is common, and building radios is common, and the galaxy has produced civilization after civilization just like ours. And suppose that the nearly impossible door is one we have not yet reached, a door that every civilization walks up to full of confidence and fails to open, something that reliably destroys technological species at roughly our stage or just beyond it, war with weapons that finally outgrow their makers, a climate quietly tipped past saving, a technology not yet invented that ends its inventors. If the filter is ahead of us, then the silence is not a coronation, it is a warning, written across the entire sky in the only language the universe has, which is absence. Every empty star is a civilization that did not make it, and we are walking the same corridor toward the same door with the same confidence. This is why the search for life elsewhere carries a strange double edge that most people never notice. We tend to assume that finding life out there would be wonderful news, but some thinkers, the philosopher Nick Bostrom among them, have argued the opposite. If we were to discover the ruins of even simple life on Mars, or microbes beneath the ice of a moon of Jupiter, it would mean that life is easy, that the early doors are not the filter. And if the early doors are not the filter, then the hard door, the one almost nothing survives, is more likely still ahead of us. In that careful, unsettling logic, the best possible news for our long future is to keep looking, and to keep finding nothing. An empty universe might be the universe in which we have the best chance of a future. Rest with how strange that is. For most of history, to be alone in the cosmos felt like the loneliest fate imaginable. The great filter quietly suggests that being alone might be the safest fate, the sign that the worst is behind us rather than ahead. Loneliness as good news. It takes a while to get used to. Of course, the great filter is one frame, not a verdict. It assumes the silence is real and the others are truly absent. And that assumption is exactly where a whole other family of thinkers steps in to disagree. What if, they ask, the others are out there after all, and the silence means something far less final than death? What if the galaxy is not empty, but only quiet, and quiet on purpose? Those answers, the ones that let us off the hook, are where we drift next. Before we let ourselves off the hook, we should sit a while longer with the lonely answer, because it is the one the hard numbers point at most directly, and because it is, in its own quiet way, the most beautiful. The lonely answer is called the rare earth hypothesis. It was laid out most fully in the year 2000 by a geologist and an astronomer, Peter Ward and Donald Brownlee, and he makes a careful distinction that most discussions blur. Simple life, they argued, might well be common across the universe. Microbes are tough. They appear quickly. They cling to scalding vents and frozen rock. If the only question were whether the galaxy holds living slime, the answer might be yes, on a great many worlds. But complex life, the kind that builds bodies and nervous systems and eventually wanders about the stars, might be staggeringly, almost impossibly rare, because to get from slime to a stargazer, a world needs not one piece of luck, but a long, unbroken chain of them, and a single missing link breaks the whole chain. Walk that chain slowly, the way you might walk a beach picking up stones. Because every stone is a coincidence we tend to take for granted. A world needs to sit in a calm neighbourhood of the galaxy, away from the crowded violent core where exploding stars would sterilize it, but not so far out that the ingredients for rocky planets never gathered. Well-behaved star, one that burns steadily for billions of years without flaring its planets to ash. It needs to orbit at just the right distance, in that narrow band where water stays liquid, neither boiling nor frozen, and it needs to hold that orbit for ages. Then it gets more particular. Our Earth has a giant planet, Jupiter, patrolling the outer system, its enormous gravity sweeping up or flinging away comets and asteroids that might otherwise have battered us into oblivion again and again. Without that distant guardian, the inner worlds may be pummeled too often for complex life to ever get a foothold. Earth also has something almost no rocky planet should have, an enormous moon, born, we think, from a single catastrophic collision early in our history. An oversized moon steadies the tilt of our planet, holding the seasons gentle and regular across millions of years, where otherwise the world might wobble wildly, lurching between scorching and freezing. A freak collision, 4 billion years ago, may be part of why you can sleep through a calm and ordinary night tonight. and the chain goes on. Earth has a hot, churning interior that drives the slow drift of continents, recycling carbon, regulating the climate over geological time like a vast slow thermostat. It has a magnetic field, born of that churning core, holding off the stripping wind of the sun. It had, somewhere in its deep past, the almost unimaginable luck of life inventing how to breathe oxygen, transforming the whole atmosphere and opening the door to large, energetic, complex creatures. And it had time, vast and uninterrupted, nearly 4 billion years of it, without a single disaster final enough to wipe the slate completely clean. The rare Earth argument is that every one of those is a low probability event, and that complex life needs all of them at once, on the same world, in the same long lucky stretch. Multiply enough small chances together, and even billions of planets are not enough. The galaxy could be drenched in living oceans, and still hold only one world, where the chain ran all the way to a creature that looks up. If rare Earth is right, then Fermi's question has a gentle answer hiding inside a hard one. The sky is silent, not because civilizations rise and fall, not because they hide, but because the road from a living world to a thinking one is so narrow that, in our galaxy, perhaps only we have walked it, not chosen, not special in any cosmic plan, just the holder of an almost impossibly long winning streak of ordinary luck. There is a feeling that comes with this idea, and it is worth letting it settle over you on a quiet night. If we truly are the only minds our galaxy has made, then we're not a small thing in an indifferent cosmos. We are the rarest thing in it. The only place, across 100 billion stars, where the universe has woken up enough to know it exists. Every human who has ever loved, or grieved, or looked up and wondered, would be part of the single thread on which all of the galaxy's self-awareness hangs. That is either the loneliest thought imaginable, or the most precious, and on different nights it can be both. The astronomer Carl Sagan, who spent his life hoping the sky was full, once said that if we are alone, it would be an awful waste of space. But there is another way to hold it. If we are alone, then this small blue world is not one candle among many. It is the only candle, and you do not leave the only candle burning carelessly. The rare Earth answer is sobering, and it may simply be true, but it rests on a tower of guesses about how rare each step really is, and we have, so far, exactly one example of a living world to reason from, which is our own. One example is not a statistic. It is barely a hint. So a great many scientists look at the same silence and refuse the lonely conclusion. The others are out there, they say. We are simply misreading their quiet, and their reasons are some of the most fascinating and most haunting ideas in the whole field. The quiet answers next. Suppose the galaxy is not empty. Suppose it is full of life, full even of minds, and the silence we hear is not absence at all, but something stranger. Choice. Caution. Distance of a kind we have not understood. This family of ideas refuses Fermi's lonely answer, and it contains some of the most beautiful and most disquieting thoughts anyone has had about our place out here. Begin with the gentlest of them, the zoo hypothesis. It was named in 1973 by an astronomer named John Ball, and the idea is exactly what it sounds like. Perhaps the others are out there, advanced far beyond us, and perhaps they know about us perfectly well, and have simply chosen to leave us alone, the way we might rope off a wilderness, or watch animals in a reserve without walking in among them. An advanced civilization might hold Earth as a kind of protected ground, observing, never interfering, letting the young world develop on its own. In that reading, the silence is not neglect. It is care. We are not being ignored. We are being given room to grow, and the quiet sky is the considerate hush of someone not wanting to wake the baby. It is a comforting thought, and it has a problem, which is the same problem that haunts every quiet answer. It only works if every single one of them agrees to it, forever, without exception. All it takes is one civilization, or one member of one civilization, to break the silence, and the hush is over. Getting millions of years of perfect agreement out of a whole galaxy of separate minds is a very tall order. Still, the idea lingers, because we cannot rule it out, and because some part of us wants it to be true. Then there is the darker cousin of the zoo, and it is the idea that, once you have heard it, changes how you feel about our own habit of shouting into the dark. It is called the dark forest. Imagine the galaxy not as an empty plain, but as a vast forest at night. Every civilization is a hunter moving quietly between the trees. In this forest you cannot easily tell who is friendly and who is dangerous. You cannot know whether the stranger across the clearing wishes you well, or means to end you, or will simply grow over centuries into something that ends you without meaning anything at all. And the distances are so great, and the time so long, that you can never wait to find out. By the time a message crosses between the stars, the sender may have changed beyond recognition. In such a forest, the writer who made this idea famous, the novelist Liu Cixin, argued there is only one safe move: stay silent, make no sound. And if you ever do detect another, the safest thing, the rational thing, is to strike before they can strike you, because they are reasoning exactly the same way about you. In the dark forest, the silence of the universe is not peace. It is the held breath of countless hunters, each one hiding, each one listening, each one afraid. And in this reading, our own behaviour, broadcasting our radio, beaming deliberate messages at nearby stars, announcing our presence to anyone who cares to listen, is not brave. It is the most dangerous thing a young civilization could possibly do. A child standing up in the dark forest and shouting, "Here I am!" Rest easy, this is a hypothesis, not a forecast, and it has its own deep flaws. It too requires nearly every civilization to think the same cold way, to never once choose connection over fear across the entire history of the galaxy. Many scientists find it more a reflection of our own anxieties than a real account of the sky, but it is impossible to deny its power, the way it takes the friendly silence of the zoo and turns it inside out into a silence of mutual dread. There are gentler, quiet answers too, and we should not leave the forest without them, because they ask less of the universe, and may be closer to the truth. Perhaps the others do not hide, and do not menace, but simply do not use radio, or stopped using it long ago. Our own loud radio era is barely a century old, and already our most advanced communication leaks less into space than it once did, carried now in cables and tight beams rather than broadcast to the sky. A civilization only a few centuries ahead of us might be electromagnetically quiet, not out of fear or policy, but simply because shouting is a phase, a brief, noisy adolescence that every technological species grows out of. If that is so, then we have been listening for campfires in an age of fibre optics. The forest is not silent. We have been straining to hear the wrong kind of sound. And perhaps, gentlest of all, they are simply asleep. The estivation hypothesis suggests that the most advanced civilizations might be deliberately dormant, waiting out the current era of the universe for a far colder future, trillions of years from now, when the background of space has cooled enough that their vast computations can run almost without cost. In that picture the galaxy is not empty and not afraid. It is resting, like a house with the lights off, its oldest minds waiting patiently for a better dawn. There is something in that idea that suits a night like this one. Even the gods, if there are any out there, may simply be sleeping. These quiet answers all share one humble, important quality. They let the universe stay full. They locate the strangeness not in some terrible barrier, but in our own narrow expectations of what a voice should sound like and how a galaxy ought to behave. And that suspicion, that the silence may be a failure of our imagination rather than a fact about the cosmos, opens the last and most forgiving family of answers, the humble answers, next. There is a family of answers to Fermi's question that asks nothing dramatic of the universe at all. No filter, no fear, no rare and lonely earth. These answers suggest something much simpler and much easier to live with. Perhaps the others are out there, ordinary and unhidden, and we have just barely begun to look, with eyes that are not yet very good. Start with how little we have actually searched. It is tempting to imagine that humanity has swept the skies thoroughly by now, that our great dishes have combed the galaxy and come up empty. The truth is almost comically humble. One of the leaders of the modern search, the astronomer Jill Tarter, offered a comparison that has stuck because it is so deflating. If you imagine all the possible places to search every star, every frequency, every moment in time, as the volume of all the water in all of Earth's oceans, then everything humanity has examined in the entire history of the search adds up to about a single glass of water. One glass, dipped once from an entire ocean. You would not conclude the ocean held no fish because one glass came up empty. And yet, that is very nearly the strength of our claim to have found the universe silent. So one humble answer is simply, we have not looked. The great silence may be less a property of the cosmos than a measure of how new and how small our listening has been. Then there is the problem of time, which is perhaps the most quietly moving idea in the whole field. The galaxy is over 13 billion years old. Against that vastness, a technological civilization, if it lasts even a few thousand years, is a flicker, a spark struck in the dark, burning briefly, going out. Now imagine the whole history of the galaxy as a single long night, and imagine civilizations as fireflies scattered across an enormous dark meadow. Each one glows for only an instant. The meadow may hold thousands of them across the whole night, but because each glow is so brief, and the night so long, two fireflies lighting up at the same moment, close enough to see each other, almost never happens. They are not absent, they are simply, nearly always, out of step in time. This is the haunting heart of that last term in Drake's equation, the lifetime L that troubled the men at Green Bank so deeply. If civilizations are common but short-lived, the galaxy could have produced 1,000 of them, and we would still likely find ourselves alone, because the others lit up and went dark long before we opened our eyes, or will not be born until long after we are gone. The silence in this reading is not spatial. It is the silence of a party where the guests arrive across billions of years and each stays, only for a moment, so that the room always seems empty even though, across the whole long night, it was crowded. And there is one more humble possibility, the most forgiving of all. Perhaps we simply would not recognize them. We look for radio, because radio is what we happen to use. In this brief slice of our own history, we look for beings roughly like us, on worlds roughly like ours, thinking roughly as we think. But a civilization a million years beyond us might be as far past radio as we are past smoke, signals. They might communicate in ways we have no instruments to detect. live in forms we would not identify as life, or have folded themselves into something so quiet and so efficient that they leave almost no mark on the sky at all. We may be a fish asking why it has never met anything that breathes air, surrounded all the while by a world it cannot perceive. There is great gentleness in these humble answers, and it is worth carrying towards sleep. They do not require the universe to be a graveyard or a battlefield or a fragile miracle. They only require us to be young and small and early and limited, which we plainly are. They turn the terrifying silence into something softer. Not the silence of an empty house, but the silence of a vast library at night, full of voices written in languages we have not yet learned to read, on shelves we have only just begun to reach. Nobody knows which of all these answers is true, the lonely one, the quiet ones, the humble ones. They cannot all be right, and they may none of them be wholly right. The honest position, the one most thoughtful scientists hold, is that we simply do not yet know enough to choose. We have one example of a living world, one example of a mind, one glass of ocean water examined, and a question older than any of us still open, still waiting. But here is what has changed in our own lifetimes, and it is the reason this is not merely an old story. We are no longer only philosophizing. For the first time in history, we have begun to actually examine specific other worlds, closely enough to ask whether they are breathing. And just last year, around one small ocean planet, 124 light-years away, the universe did something it had never done before in all our listening. It made us wonder, for a few months, whether we had finally heard an answer. That planet, and that almost answer, is where we drift next. For most of this story, Fermi's question has lived in the realm of argument. Numbers on a blackboard, ideas in papers, dishes sweeping empty sky. But in the last few years something has shifted, quietly and profoundly. We have begun, for the first time, to study the air of other worlds. And one of those worlds, in the span of a single year, came closer to answering Fermi's question than anything in the 70 years since that new Mexico lunch. Its name is plain, K2-18b. A world about 124 light-years away, circling a small, cool red star, far enough that its light tonight set out before any of us were born. It is what astronomers call a sub-Neptune, larger than Earth, smaller than the ice giants of our own system, and for a long time worlds like it were thought to be uninhabitable, crushing balls of gas. But K2-18b sits in the gentle zone where water could be liquid, and some scientists came to suspect it might be a new kind of place entirely, a Haitian world. They called it a planet wrapped in a hydrogen atmosphere, with a single vast ocean covering its whole surface. An ocean world under an alien sky. Here is the astonishing part, the part that would have seemed like magic to the men at Green Bank. We can now taste the air of such a world from across 100 light-years without going there. When K2-18b passes in front of its star, a sliver of that starlight filters through the planet's atmosphere on its way to us, and different gases drink different colours out of that light, each leaving its own faint fingerprint. By catching that starlight with our most powerful new space telescope, and reading which colours are missing, astronomers can begin to list what the planet's air is made of. We have learned to read a world's chemistry in the shadow it casts. When the telescope turned to K2-18b, it found the ordinary marks of a real atmosphere. Carbon dioxide, methane, the signatures of an actual planet with actual weather. That alone is a quiet wonder, but in the spring of last year, a team announced something that stocked the scientific world. In the planet's air, they reported a faint hint of a molecule called dimethyl sulfide. And dimethyl sulfide is special, because on Earth, as far as we know, it is essentially only one source: life. It comes from living things in our oceans, from blooms of tiny marine plankton drifting in their countless billions. On Earth, to smell that molecule is to smell the sea, and the sea is alive. For a few months, the world held a question it had never quite held before. Not as philosophy, but as data. Was there, on a real and named world 124 light-years away, the faint chemical breath of a living ocean? Newspapers ran the story across their front pages. It felt, for a moment, like the door Fermi knocked on was finally opening. And then, as good science always does, the field turned its skepticism on the claim, and the moment grew complicated. Other researchers took the same starlight and ran their own careful analyses, and found that the signal was not nearly strong enough to trust. The fingerprint of dimethyl sulfide, they showed, could be mimicked by other, lifeless molecules. The hint was real, but a hint is not a discovery, and the honest accounting came back with a hard verdict. The evidence was insufficient. To truly know, we would need many more passes of that planet across its star, many more slivers of filtered light, perhaps dozens more nights of looking. The almost answer faded back into a maybe. But notice what had happened, because it is genuinely new under the sun. For the first time, Fermi's question had a specific address. Not the whole galaxy, but one world with a name that we could point to and examine and argue about with real measurements. And we did not stop at the chemistry. Knowing how tantalizing K218b had become, scientists did the very thing the listeners had been doing since Project Ozma. They pointed radio telescopes at it, two of the most powerful arrays on Earth, and they listened across a wide sweep of frequencies for any deliberate signal, any technological whisper from that ocean world. Just months ago, this year, the result came back. They processed more than 20 million candidate signals from that one patch of sky, and every single one turned out to be noise or interference or us. No transmitter, no beacon, no voice. The careful conclusion was that if anyone is there, they are not broadcasting toward us with anything stronger than our own largest instruments. The planet that almost spoke, in the end, said nothing we could be sure of, not in the chemistry of its air, not across the radio dart. And so the oldest pattern in this whole story repeated itself one more time. On the most advanced equipment we have ever built, we looked harder than ever before, at a better target than ever before. And the universe gave us back, once again, that same vast and patient quiet, which leaves us, at the end of this long night, with the only honest place to stand, not with an answer, but with the silence itself, and the question of how to live beneath it. That, gently, is where we end. So, where does it leave us, this question asked over lunch 3/4 of a century ago, and never once answered? It leaves us exactly where Fermi's four friends were, looking up at an empty sky. We know vastly more than they did. We have counted the planets they could only guess at. We have listened, with instruments they could not have dreamed, across more of the sky and more of the radio dial than any generation before us. We have named the silence and mapped its possible meanings, and pointed our finest eyes at specific distant oceans. And after all of it, the question stands precisely where it started, open, immense, and quiet. There are really only two kinds of answer in the end, and the writer, Arthur C. Clarke, put the choice as plainly as anyone ever has. Either we are alone in the universe, he said, or we are not, and both possibilities are equally terrifying. Sit with that balance gently as the night settles. If we are alone, then this small world is the only place the universe has ever woken up, the only eyes it has, the only love, the only grief, the only wondering. Every star you can see and the 100 billion you cannot would be a kingdom with no one in it but us, and the responsibility of being the single thread of awareness in all that dark is almost too large to hold. And if we're not alone, if the silence hides a galaxy full of others, then we are surrounded, watched perhaps, or ignored, or simply out of step in time, sharing the dark with minds we may never meet and may not survive meeting. A crowded silence, and a lonely one, both true to the same empty sky. But there is a third thing to feel beyond terror, and it may be the truest thing this whole long question has to teach. Whichever answer is real, the silence makes this particular night, on this particular world, extraordinary. While you are lying here, you are doing the rarest thing we have ever found anywhere in the cosmos. You are a part of the universe that is awake, a small, warm, conscious corner of a vast, cold, dark wondering about the whole of it. That may be common, repeated on 1,000,000 worlds across the galaxy. Or it may be, as far as our entire galaxy is concerned, happening in only one place, which is here, which is us, which is you. The men at that lunch table went back to their work, and the question outlived every one of them. It will almost certainly outlive us too. Somewhere out in that dark, the dishes are still turning, still listening. Tonight, while you fall asleep, patient machines pointed at the quiet, waiting for the 72 seconds that might come or might never come. There is something deeply restful in that image. When you stop fearing it, the search goes on without you tonight. You do not have to keep watch. You can let the great dishes listen, and the slow stars turn, and the questions stay open, and simply rest inside the mystery instead of needing to solve it. Maybe one night, long after this one, a signal will arrive and not fade, a voice in the dark that repeats and repeats, and finally answers the man who asked where everybody was. Or maybe the silence will hold forever, and the answer will turn out to be that we were the ones the universe was waiting for. We may never know which. Almost certainly we will not know tonight. And tonight that is enough. The sky does not need you to solve it. It only asks you to look up, now and then, and feel the size of the question, and then to close your eyes and rest, knowing that you are the part of the cosmos that got to wonder at all. The stars will keep their silence, the dishes will keep their watch, and the oldest question we have ever asked will still be there in the morning, patient as ever, as patient as it has always been. So for now, you can simply let it go, and let the galaxy turn without you, drift gently out into the quiet, where the whole vast and silent universe is holding still around you just for tonight. Sleep well, and we will keep listening for you.